Hello guys, we are Helping Hands from NIT Trichy. We have taken up the problem statement number 1581, which is development of cost-effective myoelectric processes. The problem statement stresses on cost-effectiveness part, and it is a myoelectric processes. So, coming to the problem statement description, what does the problem statement expect us to do? The problem statement has asked us to make an externally powered prosthesis which is controlled by muscle contraction. So basically, we're getting the signals from the muscle movements. So the signals are taken up at the muscles as small voltages, and it is captured through an EMG sensor. And this is what is like most common in the market. So the important feature of this process should be its grasping pattern, and it should be able to perform a large number of grasping patterns, and it should be also cheaper. So, and the problem with the existing solutions is that they are all expensive, and when it becomes like high end, it becomes challenging for the patients to operate it, and the features are also sometimes limited and doesn't work precisely. So what do they expect from us? So they want us to fabricate a prosthesis, myoelectric prosthesis, with all the circuit and all the sockets and the fitment required, and design it such that it is cost effective. So the most important feature of it should be the grasping pattern, and yeah, that's basically it.
The EMG controlled prosthetic hand that we have developed uses a linkage mechanism based on toggle positions and graphical linkage synthesis to create a natural movement of human fingers. This design approach makes the prosthetic both efficient as well as highly functionable. The linkage mechanism works by translating input forces such as muscle signals captured through EMG sensors into complex finger motion. The clever usage of toggle positions allows the prosthetic fingers to lock into places when fully extended or flexed, maintaining this position with minimal energy. This is crucial for tasks like grasping or holding objects, when the hand can remain in a position without requiring constant motor power, increasing energy efficiency and extended battery life. Graphical linkage synthesis is employed to design the precise motion of the finger. This method allows the linkage system to fine-tuned so that the prosthetic finger move in a ways that closely mimic human hand movements. Whether grasping, pinching, or fully extending the fingers, the system ensures smooth and natural motion, making the prosthetic feel more initiative for the user. The key benefits of this design includes efficient energy use, natural motion, and durability. The combinations of toggle-based linkage mechanism and graphical synthesis offers a cost-effective solution to creating a prosthetic hand that is both adaptable and user-friendly. It enhances mobility and gives users great autonomy, making the prosthetic hand an essential tool for improving daily life activities.
A spherical parallel manipulator is a type of mechanism where multiple arms work together in parallel to control the orientation of a platform or a joint. The SPM provides rotational movement along multiple axes, usually the 3 degrees of freedom, that is, pitch, roll, and yaw. The SPM consists of 3 stages, where each stage rotates individually to control a link, and combination of the rotation of each of these stages will result in the desired orientation and rotation. The benefits of SPM over the traditional setup is that it provides better load distribution. SPMs provide better load distribution as it has multiple links and reducing the strain on individual actuators. This results in more smoother and controlled movements and increases the durability of the system. And SPM also provides increased precision and stability. The parallel architecture of a SPM offers superior control and accuracy, which is essential for the fine movements that's required by a hand. It also has a lower energy consumption since each motor can work less than compared to that of the ones present in a two-axis system. It's comparatively lightweight and more compact, and also is more durable than other existing solutions.
We have incorporated ML in our project, and there are two main reasons for it. One is the accuracy, and the other is the calculation tediousness. When we are doing the normal calculation, the calculation might become very complex or complicated because there are 6 EMG sensors that we are going to use, and each of them will have a different value for the same grasping pattern, and because they are going to be placed at different positions of the hand, and the values will also change between each reading due to the noise or the other external factors, and ML can account for all of these. The accuracy is also high for ML because it can take in a lot of training data set, and we can and in our model we have actually achieved a training accuracy of 89%, which is really high, and this cannot be replicated through calculations. Coming to what we have exactly done in our project, we have made use of 10 fully connected layers, and it has 8 input classes and 8 output classes. So this was done based on a data set which is available online. And that particular data set used 8 EMG sensors, while we'll be using 6 for our project. The 8 output classes show the 8 grasping patterns that the dataset had and that we could train it on. Each layer had a ReLU non-linearity function, and the last layer, of course, had a softmax function because we are doing non-binary data classification here. Adam optimizer was used as the optimizer, and cross entropy loss was used for calculating the loss function. We did batch processing in order to speed up the learning process and also get a better learning. Thus, after training, we got about 89% train accuracy, 87% validation accuracy, and 87% test accuracy, which is really good and can be scaled up further. What we plan on doing is to make use of a combination of CAN and CNN, which is an autoencoder and a convolution network. So this is very promising, and it can give accuracies up to 99%. We'll be using 6 EMG sensors, and we're planning to also get the data set on our own by creating a custom data set. A windowing method can be followed in order to increase the number of samples in the data set to get a better training. So this means the data will be like customized and will be like personalized to that person. So this looks very promising, and this will be used by us.
Moving on, the control system of the prosthetic arm begins with the sensors reading signals from the user's residual limb, amplifying and conditioning them before inputting them into a machine learning model. The ML model classifies these signals into grasping patterns, which the microcontrollers use to compute the inverse kinematics and send appropriate signals to the servo motors. The arm is also equipped with an IMU or an initial measurement unit for orientation tracking and a force resistive sensors for monitoring upright force, providing the feedback to the microcontroller. Haptic feedback is provided through vibrational motors placed on the user's residual limb.
So moving on to the EMG sensor part, EMG sensors are one of the most important parts of this prosthetic arm. The EMG sensor detects the signals of muscle contractions to predict the motion of the hand. Main functions of these EMG sensors includes detection of signal, amplifying the signals in the range of millivolts to signals of higher voltage range for further actuation purposes, along with noise reduction and rectification. Each of the EMG sensor comes with 3 electrodes, namely 2 recording electrodes and a reference electrode. In our prosthetic arm, we decided to use 6 sensors to detect the most precise signals. Adding on to the placement of electrodes, instead of placing the electrodes uniformly around the circumference of the forearm, we will be placing the electrodes on 6 targeted muscle groups which plays distinct roles in hand movements. Also, this targeted sensor positioning allows us to reduce the physiological noises and other signals from interfering. To make the arm cost effective and to reduce the number of electrodes and for various other reasons, we decided to modify and replicate the EMG sensor. This enables us to reduce the number of electrodes from 18 to 13 and also provides us ways to work with the targeted muscle and the output signal. So given below is the first design iteration of the replicated EMG sensor. So this circuit consists of an instrumentation amplifier followed by an operational amplifier and a capacitor to filter out the DC component, which is followed by an operational amplifier and a precision rectifier which is used to convert AC signals to DC signals. So it is followed by some final amplification and smoothing out of the rectified signal.
So the output signal is now ready to be interpreted by an microcontroller, and which can be used for further actuation purposes.
Cooperating ML model helps to collect data from the EMG sensor more accurately. Greater inclusion in society and enhanced career opportunities are made available for the amputees. Implementing toggle positions can facilitate precise control over individual fingers, and control systems are developed accurately. There are many challenges that are found while making of this product. One is the inverse kinematics in accompanying SPM is very complex. Although most of the components are waterproof, the electronic components or the circuits that are embedded in it are not. The weight of the batteries are taken into consideration because more the number of batteries can increase the weight of the prosthetic arm. This can be reduced by optimizing the number of batteries.